let's move on to our first invited paper presentation for today by Bruno Loureiro at University Paris, Saclay. And he will talk about precise asymptotics for phase retrieval and compressed sensing with random generative priors.
So thank you for the organizers, especially for putting me onto this session, because after these two invited talks, I could even skip my intro, but for the sake of cohesion, please bear with me. So I'm going to be talking about the joint work done in collaboration with Benjamin Aubin and Lenkes de Borova from the University of Paris-Saclay, and with Antoine Baker and Florent Jacala from the École Normale Supérieure. So just like in Professor Ng's setting, we are going to be talking about inverse problems. So these are problems in which you have a signal, X here, and RD, which are sent through a channel, usually a noise, to generate some observations, which are then handed to the statistician. And the statistician needs to recover the signal X with as few measurements as possible, as parameterized by the sample complexity, which is the ratio between the observations and the sample dimension. So some examples beyond all the examples already given by Professor Ng and Professor Malat. We could think about denoising an image where a corrupted image is given to the statistician who needs to separate the noise from the picture. We could think about matrix factorization, which is an example where we have one leading direction in a Gaussian cloud, and we need to distinguish this direction from the noise. And probably the most well-known example is compressed sensing, where we have a compressed representation of the signal, which needs to be decompressed. And its usual cousin, which is a phase retrieval, which beyond the compression, we are adding an absolute value which cues the information about the sign of the signal. So in these kind of problems, different from the previous talks, the question I would be interested here is about the statistical and algorithmic limitations of reconstruction of signals, and especially in the case where the signal is structured. So the structure can be either by some previous knowledge of the signal, or either by some physical intuition, as we saw in the previous talk. And one of the common structures discussed already here is sparsity, where we have, for instance, of the D components of the signal, we have K of them, which are only non-zero. And we're trying to use this knowledge to leverage reconstruction. So for example, we know that many signals like images or sound are sparse in the already mentioned wavelet and Fourier basis. So these are some examples. So in sparse coding, the beginning of the analysis starts with the assumption that we know there exists such a sparse basis. But ideally, as Professor Malat was explaining, like I would like to learn such a basis, and probably the best basis possible. For instance, by training a deep neural network on the data set of the same class of the signal, or using the scattering transform. With the recent advance in deep learning, becomes a fair question to ask whether this compressed representation learned, for example, by a neural network can help in signal reconstruction tasks such as compressed sensing, for example. So just to be clear about the setting I have in mind, I imagine someone somewhere in the earth, probably in a big tech company with huge computing resources, is going to train a generative networks and is going to upload on GitHub. And someone else in the other side of the globe is going to get this network, and this person is trying to solve, I don't know, let's say a compressed sensing problem, and is asking the question, is it possible to leverage the learned deep representation of the image, for example, for image reconstruction, for example, using like this information as a prior? So of course, we are not the first one to ask this question. There are many works in the literature, both from the practical and from the theoretical perspective. And there was even a workshop last year in EURIPS all about that from both perspectives, theoretical and practical. So before I dive into the results of this paper, which is about compressed sensing phase retrieval, I would like to speak a little bit about some of the things that we have learned in terms of matrix factorization. So last year, we have shown, like in a work that we submitted to EURIPS, that for different than sparse priors, in which we have a considerable statistical to algorithmic gap in the reconstruction performance, generative priors defined by random deep networks with the common architecture, so I'm thinking here about some ReLU activations, are able to attain the optimal statistical performance in this problem. Moreover, we are also able to leverage this knowledge of the structure given by the network to develop modified spectral algorithms that beats PCA and achieves exactly the optimal statistical performance predicted by the Bayesian analysis. So the question we would naturally ask is, how generic is this behavior among other inverse problems? So in this paper, I'll be focusing on the compressed sensing in phase retrieval, and especially in phase retrieval, where the absolute value, for instance, makes the problem non-convex and much harder to solve. So both these problems are examples of a more general linear estimation problem in which the signal is drawn from a known prior. So here the prior is going to be either a sparse representation or one of these deep random networks I was mentioning. Then the signal, once it's generated, is multiplied by a random matrix A, in which my setting is going to be a Gaussian IID. And up to a noise term is going to be passed through a nonlinearity and handed to the statistician. So in this setting, for instance, the compressed sensing is given by taking phi to be the identity, and the phase retrieval by taking phi to be the absolute value. Then the statistician observes the signal, gets the observation and tries to reconstruct the signal with the knowledge that she has from the phi, A, and the prior. So in particular, we're going to be interested in the setting where the number of samples and the dimension of the signal goes to infinity, while the sample complexity that I previously defined stays of order 1, which is a high dimensional regime. So the behavior for sparse priors in this context is well exemplified by this work of Barbier et al., who showed that for a signal drawn from a distribution with a density rho of non-zero Gaussian components, there is a gap in performance, exactly as I was mentioning, between the best non-polynomial time algorithm and the optimal statistical performance. So this gap is particularly huge for the phase retrieval problem, which is exemplified in this phase diagram, which is a plot on the sample complexity against the sparsity plane, which shows that even for small sparsity, we have a big gap between tractable recovery and statistical performance. So the question we want to ask in this paper is, can we draw a similar picture for the random deep generative priors given by a random network with generic activation sigma, which could be different in each layer, but also we could take all to be the same. So for our analysis, there are two pillars. So first, statistically, it's important to stress that we are able to access the optimal reconstruction performance by looking at the Bayesian estimator for the signal, since all the knowledge about the prior and of the channel are given. Of course, computing this estimator is intractable, but thanks to techniques of statistical physics, we can reduce the problem of estimating the performance of this estimator to just a scalar extremization problem, which is given by a single letter formula, which is very easy to evaluate in a computer. So in this formula, you can see that the sample complexity appears, the compression on each layer appears, and also we have some potential functions that depends on both the task we're trying to solve, whether it's compressed sensing or depends on the nonlinearity phi that I have previously introduced. We have a term that depends on the architecture, and we have a term that depends on the latent distribution of the signal. So here I'm not giving the full expression for these potentials, but you can find in the paper because it's quite cumbersome. So it's also important to freeze out that this formula has been proven in the case of a single layer generative prior in this work by Gabriel and all in 2018, and has been recently derived previously in a work by Manuel and all in 17. So the other pillar of our analysis is the algorithmic part, right? Because I'm here, as I previously said, I want to compare the statistical to algorithmic performance. So to assess the algorithmic hardness of the problem, we are going to be using an approximate message passing algorithm, which is the best non-polynomial time algorithm in the generalized linear estimation problem with random weights. So a few words about this algorithm. It can be derived systematically from belief propagation, and very importantly, it can be tracked analytically in the high dimensional limit. And I mean, if you don't like the algorithm itself, you don't even need to code it. You can just download a robust implementation, which is available on GitHub. And the implementation is just like Keras or PyTorch, which in the sense that is modular. So you can compose any tree of inference problems node by node. So if you're curious, do check out. So let's now dive into some of a selection of the results. So in this slide, I'll focus on the phase retrieval, which is the harder task. But this story also holds for compressed sensing. So here we're going to consider two generative architectures, linear and ReLU. Solid lines show the prediction of the formula, and the dots are the finite size runs of the algorithm. So for the linear case, we can identify a weak recovery transition below which the reconstruction is not possible, which is not present for the ReLU because the ReLU prior is more informative. But when it's present, we also have a closed form expression for the weak recovery threshold. So in both cases, we can identify a gap between the point which can perfectly reconstruct the signal statistically, which I call alpha IT here, which is 1 for the linear case and 0.5 for the ReLU. Which is what can also derive analytically from the formula, and the point at which the approximate message passing algorithm can recover. This is exactly the gap which I was mentioning previously. And this is best seen in terms of the phase diagram that I have also introduced previously in the sample complexity against compression plane, where on the left, for the linear case, we have also traced the curve of Barbier and all, showing like the difference in gap between the sparse and the generative networks. So we can see that the gap is much, much lower in the case of the generative networks at the same level of compression or sparsity rule. So in particular, the gap can be made very, very small by increasing the depth and the layer-wise compression, which is an observation which is in line with the previous works and on this topic, both from the practical perspective and also theoretical that I previously mentioned. So I'm going to conclude. So in this work, we have derived the statistical and algorithmic performance of generalized linear estimation with random deep generative priors. We have shown that in the context of compressed sensing and phase retrieval, these priors have comparatively smaller statistical to algorithmic performance gap, and which can be made almost zero by increasing both the depth and the compression factors. And to finish, I'm going to leave you with a provocation, which is, are generative priors the new sparsity, or they are better than sparsity? So this remains to be analyzed in more concrete settings. We actually have training and not only random networks, but it's a good start from the theoretical perspective. So thank you. If you are curious about the details and the other results which I didn't have time to mention, please do check our paper on archive. Is available on this link. Thank you.
Thank you, Bruno. You finished just on time. One question we have here is, do these sorts of results extend beyond phase retrieval? If you think of phase retrieval as, you know, a rank 1 matrix recovery from sort of rank 1 measurements, do they extend to sort of more general low rank matrix recovery from rank 1 measurements?
So when a case where the sensing matrix is a rank 1, has a rank 1 structure, you mean? So these results specifically that I presented here, no, but we can use similar techniques to analyze this problem. So I have in mind especially a work done in our group by Francesca Mignaco, which has exactly this calculation for the case of a rank 1 or rank K in general, as long as not extensive. Exactly in this setting. So so the question is yes, but not in my talk.
Thank you. And one more quick question. How is the information theoretic bound for the generative prior calculated?
By that I understand like the sample complexity, the information theoretical sample complexity. So in these problems, we can extend an argument already used in compressed sensing by Tao, Candes, and Bono, like in which it's basically a counting argument on the inversibility of linear systems. And then it can be extended to the absolute value by just some inequalities, simple inequalities. But it's basically an extension of a known argument of inversibility of the matrix, layer by layer.
Can I add just one comment about my talk?
Absolutely.
Okay. So because I got this question on Slack, and I think it's also related to one of the Q&A questions which I haven't answered yet. Just to clarify, and as a question of liability, since we're live, the networks that we consider in the work, they are random, so they are not trained. And that's because we want to have a sharp statistical and algorithmic analysis of the limitation of reconstruction of the signal in this setting. So that's kind of a trade-off you pay for wanting to be precise, like being able to identify specific thresholds. You need somehow to have simple generative models which come from random ensembles. So just to clarify, they are not trained. Of course, we'd like to analyze train ensembles, but then we wouldn't be able to specifically
have statistical and algorithmic thresholds.
Thank you, Bruno. And while we have you, just one more question from the chat box. Could you comment further on the impact of different GAN priors and the results and on the results and the algorithmic gaps?
So that's a good question, because the relation is not simple between the statistical and algorithmic gaps with the architecture. So as I said, they are random architectures. And you can see that like what defines the ensembles that we are using is actually the activation functions at each layer and the prior that you use for the latent dimension. So like if you just fix that to be Gaussian, just as people that train GANs do, this will depend on the activation. So for example, we can observe that ReLU activation, so if you choose ReLU all throughout the network, they are pretty good in terms of recovery performance. However, we also know that, for instance, if we get a ReLU architecture very deep with some strong bias, we would induce a sparsity, which would create an algorithmic gap, as I said, for the sparse signal case. So it's not trivial at all, the relationship between the performance, the algorithmic performance and the architecture. But it can be analyzed once the architecture is fixed. You could analyze using the formula, but there's not like a generic message that we can extract from it in this sense.